Proceed now to the next presentation entitled Trapped on Seashore Seaborne Evacuation and Impact of Exposure to MP2.5 Live Demonstration of the urbanEXODUS Large-Scale Evacuation Model. Dr. Philippidis will be the presenter. The floor is yours.
Hello, can you confirm you can see the presentation and hear me?
Yes, it's perfect. You may proceed.
Great. Hi, my name is Lazaros Philippidis. I'm part of the Fire Safety Engineering Group of the University of Greenwich. We specialize in mathematical modeling and experimental analysis of pedestrian dynamics, evacuation modeling, and fire effluent modeling as well. The two main tools that we produce the Exodus evacuation simulation tool, and we produce also the smart fire modeling tool that actually that allows you to model a fire influence within a closed environment. You can see here some examples of previous work that we've done, but I'm not going to go through them. There's other things that are a bit more interesting. With regards to Exodus, the evacuation model, it's a micro-simulation agent-based model. It's capable of simulating hundreds of thousands of individual agents in a variety of environments, including buildings, ships, airplanes. And for that purpose, we have designed different variants of the Exodus model. Again, here you can see examples of work that we've conducted on various environments. And what is relevant to this speech is the large-scale model that we've developed, urbanEXODUS. So let me just, I'm not sure if you can, just a second. Okay. Now we've been talking a lot these days about disasters and crises and incidents. Now, for an incident to become a disaster, it has to involve a community. So the common factor in all socio-natural disasters or crises is the human element. And it's essential to understand the human response and behavior during these incidents that become disasters. And the modeling tools will see how they can help us to determine the likely outcome of such incident that eventually becomes a disaster. So evacuation modeling tools, they offer you insights that reduce the complexity of the evacuation process. It allows for risk-informed decisions to be made when planning or managing a crisis. And the model that we've developed, urbanEXODUS, attempts to address all these points. Now you may ask how complex this process is. Well, it's pretty complex because it involves a lot of agents. It involves, of course, the population, the community. It involves the first responders, secondary responders. It involves the crisis managers. It involves interactions with the environment, the landscape, and of course with the hazard, for example, the wildfire. Now, for this specific talk, I'm going to concentrate on a live exercise that I conducted in Rhodes. It was part of the last exercise for the Horizon 2020 InPrep project. And the scenario that we had to examine for this particular demonstration was a traffic accident that escalated into a wildfire, causing a multi-modal evacuation of the Calithea Springs region. So for this evacuation scenario, we will see that the population had to evacuate by foot, using vehicles, or using boats. So the methodology here is to use urbanEXODUS to represent the multimodal evacuation of the region, and at the same time determine the effect that the wildfire has on the population and the smoke plume has on the population as well. Okay, so with regards to the scenario, the first accident that took place caused the main road of the Calithea Springs region to become completely congested. Shortly afterwards, a second incident took place that actually started the wildfire. Eventually, the wildfire consumed the entire forested area. With regards to the fire data, we received the fire propagation results from our partners, IES from Italy. They used the model FARSIGHT to determine how the wildfire would progress within the forested area. And from the same partner, we received the smoke plume data. They used, in this case, a HARP split model to determine how the smoke plume will develop. Now, regarding the fire data, it estimates at each time step the area that has been burned. And we'll see how we use this information when the simulation will be presented. With regards to the plume data, it estimates at each time step the various particulate matter 2.5 concentration levels that are present within the smoke. And we'll see how this smoke affects the individuals. In this particular scenario, the model predicted levels of PM2.5 at 150, 300, 600, 1,200, and 2,400 micrograms per cubic meter. So for this scenario, we developed a model that actually, well, it's a fractional dose model that determines when the effect takes place. And what I mean here with effect is when the individuals within the simulation are exposed to the air quality guidelines that were set by the World Health Organization. These guidelines were updated late last year. They were updated, I think, in September 2021. And the level that the World Health Organization set was that for a 24-hour period, the average exposure to particulate matter 2.5 should not exceed 15 micrograms per cubic meter. So for this particular level, the European Air Quality Index sets the conditions as fair. So this is where the World Health Organization put the limit. So people should not be exposed to values greater than that. So we developed this model in order to find out what will happen to the simulated agents during the simulation run. So this is the list of the events that took place in this scenario. We have the first accident that took place at approximately 4 minutes. The main road was completely congested. The main road is this blue line here. Some passengers that were involved, bus passengers, tourists that were involved in the accident walked towards the forested area to wait for the next bus. A second accident took place in the northern part of this area, causing the wildfire to start. The pedestrians within the forested area started to move away from the fire and towards the north exit, the south exit, and the seafront. And eventually, the wildfire consumes the entire area, and the evacuation is affected by that. So the two main exit points from this area: the northern part of the road, the southern part of the road, and there are also 4 locations with boats that allow a seaborne evacuation to take place. We had to make some assumptions regarding the boat capacity, the boarding rate, and the waiting time for the next boat. These were all parameters that we received from our partners in the project. Just getting rid of the mobile phone. Okay, the population number in this area is shown here. For example, here there are 100 people in the seafront over there, 200 people over there, and so on. The total number of people as pedestrians or passengers and drivers in vehicles was 3,125. And here we can see now the video of the simulation running. Of course, here I've sped it up significantly. Otherwise, it would have taken approximately 2.5 hours to run at real time. So this is now much faster than real time. The dark blue dots on the main road are vehicles that are leaving the area. The rest of them that don't move are trapped in congestion. The rest of the dots, the pink dots here, the green ones, the cyan here, the pink ones here, and these blue ones as well are pedestrians, they're people, they're individual people. And we see how the scenario evolves. We're still early a bit, 25 minutes into the simulation. Okay, now, this is now when the second accident takes place. The fire will actually has started now. Here you can see the fire contours. This is how far away the fire has expanded within a few minutes. The gray lines here, the gray contours here, they represent the smoke contour. And as the simulation is running, the agents, you can see them traveling towards alternative escape routes. So they cannot use these boats because they'll be soon consumed by the fire. They change direction. So we can see how the fire and the smoke plume affects the evacuation process, making the agents redirect away from the fire. The vehicles are trapped, they cannot go away, so the vehicles are also burned by this fire. Lots of time, actually. Okay, let me just take it a bit forward. The evacuation takes place in this area as well. The agents are using the boats to leave this area. There are a few agents here as well, but they leave the area. And the resorts were evacuated as well. Maybe I actually jumped too far. There you are. You can see the resorts being evacuated as well. And the reasons why these hotels are evacuated is because there was a truck carrying LPG in this area, and there was fear that this truck perhaps would explode due to the wildfire approaching. So because there was this hazard over there, it was decided that these hotels and resorts should evacuate the people that stayed over there. Okay. Okay. So what we see here this is the evacuation graph that shows us the number of people out over time. So this is standard evacuation graph for any kind of scenario. The gaps that you see here in the graph represent periods of times when nobody could evacuate. And these specific periods here represent the agents within the Kalithea Springs region waiting for the boats to arrive back to pick them up and allow them to evacuate from the area. The vertical lines here represent when specific events took place. The first accident took place within 1 minute of the scenario. The second accident took place 26 minutes after the start of the scenario. At 29 minutes, the actual evacuation started. So all the people that are leaving this area at this time, between 0 and 29 minutes, represent background traffic that comes in and out from that area. And the overall evacuation time is approximately, in this case, 2.5 hours. And we're talking about approximately 3,000 people. So a bit more specific here, as I said earlier, the total number of people for this scenario was 3,125. The evacuation time for this scenario took 2 hours and 28 minutes. The evacuees were 2,931. That's 94% of the entire population. But 6% of the population was not able to evacuate. They got engulfed by the fire and they got trapped in that area. So we have we have 194 fatalities. We have 194 trapped people, which are considered to be fatalities because they cannot escape from the wildfire. With regards to the vehicles, 45% of the vehicles managed to escape, obviously with the drivers, but 55% were stuck in the area. With regards to the exit usage, 5% of the evacuees used the northern exit, located there. 31% of the population used the boats, so a very significant number used the boats to evacuate. And the south exit was used by 64% of the population. Now, with regards to how people were affected by the particulate matter, as I said, we developed that novel model to determine the effect of particulate matter on the evacuees. And what we found out was that for this scenario, 84% of the population were not exposed to smoke at all. 1% received a dosage that was less than the air quality guideline that the World Health Organization set. But 15% of them received a value, and we're talking now about 426 people, significantly higher than 1, which corresponds to the air quality guideline set by the World Health Organization. Now, more specifically, they received the average fractional dose that they received was on average 7.6 times the guidelines set by WHO, with a maximum value of 28 times the permitted dosage. So for this kind of exposure, it is expected that some of these evacuees, we're talking about survivors here, we're talking about people here that actually managed to evacuate from the area, but it's expected that some of these evacuees will experience significant health problems, including respiratory problems, cardiovascular problems, and cerebrovascular disorders. And perhaps some of them will actually succumb to this exposure, to their injuries due to this exposure. So the total number of fatalities might actually increase following the successful evacuation of these people. So we thought that the points that I want to make for these kind of models is that without modeling, without evacuation simulation, it is practically impossible to obtain the level of information and insights that they can give you. It's impossible to determine evacuation times, injury levels, effect of the hazards. It's very difficult, and as I said, perhaps practically impossible to test and assess the validity of existing or complex and extreme what-if scenarios. If you want to test your procedures or examine what-if scenarios, crazy scenarios that we came up with, how are you going to test them? It's probably impossible to conduct real trials with thousands of people. So evacuation modeling tools actually allow you to conduct these studies. You can actually study these scenarios and find out what is the likely outcome of a crisis or of a scenario that you design. And the ultimate goal, of course, for using these tools is to save lives, times, and resources, and eventually to increase the public's confidence in the preparedness of the authorities and the local communities, increase and strengthen resilience for future incidents that will most definitely happen. Thank you very much. This was my presentation. If you visit this URL, you can find all the references for this work. If you have any questions, I'll be happy to answer them.